you for joining me today and thank you for having me here. So I'm going to talk about how studying the morphology of extragalactic jets in the X-rays can help us understand, understand how they produce X-rays and in turn allow us to constrain their jet kinematics. I'll briefly describe the contributions of Chandler to our understanding of these jets and how Axis is going to heavily improve upon it. So this is the infamous M87. In fact, this is the first jet ever to be recorded. Excuse me, for some reason. Yeah, got it. So in fact, this is the first jet ever to be recorded in the literature dating back to 1918. These jets carry energy and momentum from the central parsec scale regions of the supermassive black hole out to kiloparsecs and often to megaparsec scales. They encode the history of supermassive black hole activity during the jet's lifetime, which is often estimated on the scales of a few mega years. We have detected several jets so far in the radio, also in the optical and also in the X-rays. So why do we need to study them? They are interesting, definitely. Uh, they can stimulate or slow the rate of star formation. These jets often extend up to megaparsec scales from the host galaxy, and they can also stimulate the growth of entire galaxies at this far away from the actual host galaxy. They can accelerate high energy cosmic rays, and they possibly may account for the large fraction of the spectrum above the knee in the universal spectrum. Their lobes or cocoons resulting from these jets, they can float away from the host galaxy and they get assimilated in the circumgalactic medium, which they heat. They could have possibly contributed to most of the intergalactic magnetic fields. And more importantly, they act as cosmic beacons. They could potentially establish the dominant energy environment in the early universe. And such jets at high redshifts, of course. Such jets, they probe the physics of the earliest actively accreting supermassive black hole systems. So over the last 50 years, we have made several advances on theoretical. Oh my God. No. We have made several advances on theoretical, numerical, and observational fronts, but we still don't know a lot about them. We don't know how they are launched from the central parsec scale regions of the black hole. We don't know how several of these jets remain extremely collimated on megaparsec scales. We also don't know their exact plasma composition. Is it pair plasma or is there any hadronic component? We also don't know how fast these jets move on kiloparsec scales. And we also don't know if these jets have some form of velocity stratification. We also don't quite fully understand the direct connection between the supermassive black hole activity and the existence of jets. And also, we also don't quite understand what could result in the diverse morphology of these jets. So, before the launch of Chandra, multiple jets were detected in the radio and also in the optical, but even nearby jets were barely resolved in the X-rays. And it all changed when Chandra was launched in 1999. So right after its launch, the ground team wanted to calibrate the instrument using a distant quasar called Park 0637-752. And based on the available low frequency data at that time, they expected it was going to be a bright point source, but unexpectedly they found a 100 kiloparsec long X-ray jet. Now, Chandra has detected around 200 jets so far, and several powerful of these jets, or the FR2 type, they show such anomalous X-ray emission. So why do I say it's unexpected? We can understand it by taking a look at their ACDs. These jets generally emit in the radio and sometimes also in the infrared. And this low energy part of the spectrum is generally explained by one or two synchrotron components. If we extend this low energy component into the X-rays, we expect no detectable level of X-ray flux. But in reality, these jets shine extremely bright in the X-rays, requiring a separate spectral component. Other low-power jets like M87 that I showed earlier, they also have a low low energy spectral component with the which can be explained in synchrotron, but typically they can be extended to X-rays, and the observations are consistent with that extension. So, so I'll only focus on the anomalous X-ray jets. So initially, in the case of Park 0637, the authors considered a few different mechanisms to explain the observed X-rays. They considered thermal emission, but then it required unphysical conditions and it was ruled out. Then they considered inverse Compton scattering of the cosmic microwave background by a non-relativistic jet, and it underpredicted the observed flux by about 2 orders of magnitude. So it was ruled out. And synchrotron self-Compton had a similar problem. Uh, so what could be the emission mechanism of these X-rays? So until recently, the inverse Compton scattering of the cosmic microwave background was predominantly used to explain these X-rays, but this time with a highly relativistic and a closely aligned jet. It's able to explain the observed X-ray flux, but it has several observational shortcomings. For example, it predicts anomalously high gamma ray emission, um, and which is well above the Fermi limits of several jets. Or radio observations, they employ only mildly relativistic jet as opposed to highly relativistic jet required by this ICCMB model. Alternatively, they can be interpreted as synchrotron emission from a separate high energy population. This population has energies much higher than uh, what is required to produce the radio to optical emission. Now, this relaxes several uncomfortable constraints required by the ICCMB model, but again, it has its own problems. The first question is, why should there be a second electron population? And also, sometimes we need a cutoff of electron energies at a few TeV so as to not overproduce the observed optical or infrared emission. The main problem here is, although both these mechanisms can explain the observed X-ray flux, um, they predict orders of magnitude differences in the jet power that is fed back into the host galaxy and the galaxy cluster. Now, jet power is extremely important to understand the impacts of jets on galaxy evolution. Now, besides doing these kind of spectral analysis, we can actually study their structure to obtain further clues. So this is a typical X-ray jet with a radio contours overlaid on the top. The bright features in the jets are called knots, and the terminus is called the hotspot. Now, generally, when ICCMB model is used to interpret these X-rays, they are considered with the one zone assumption. That means roughly the same electrons that produce the radio also produce the also produce the X-rays. But in only a few cases, structure has been invoked in synchrotron, but synchrotron interpretation generally don't involve any kind of structure. So let's take this knot, for example. If you look closely, the X-rays peak and decay before the radio does. So this uh, uh, so this is quite contradictory to the spatial coincidence that is predicted by one zone ICCMB. On the other hand, synchrotron doesn't predict any offsets by itself, but in principle, we can move the emission zone upstream of the radio. So these offsets, besides introducing a direct constraint on the multi-wavelength structure of these knots, we can also use them to understand how knots form. So in detecting offsets, we generally face two kinds of jets: a high count jet uh, and low count jets. So in high count knots like this one, we can use a centroid to test for an offset, but it doesn't account for interference from surrounding knots or the bright AGN core or the background. In the uh, in the case of low count jets, emission from surrounding sources can not only induce an offset, but they also can induce a false detection. So these two problems, namely detection and localization, can be addressed using a statistical tool called LIRA, or low count image reconstruction and analysis. Um, Briefly, it determines the emission in excess of a baseline that is required to reconstruct the observation. So baseline can contain any known sources of emission like the bright AGN core or the background, and we can sample the output from LIRA to create images of this excess emission. And we can use that output in several different ways. Like we can use it to test the significance of an offset or significance of emission, or even average them to produce a baseline subtracted deconvolved image, which essentially gives us the underlying structure in the jet. So for example, in this case, this is a pretty low count jet, but we can reconstruct that structure using LIRA's output, which is shown on the right. We can also obtain similar results in the case of high count jets. In this particular case, the original X-ray observation doesn't show any evidence for a knotty structure in the jet, which can be falsely interpreted as evidence for ICCMB. Because in ICCMB, the X-ray emitting electrons have much lower energies than the radio ones, so we can expect a smooth profile. But the deconvolved image actually shows a clear knotty structure in the image that correlates well with the radio. So after analyzing the entire currently available sample of 200 jets, some interesting results showed up. So I want to quickly mention the current state of offset. So of about 200 jets detected by Chandra, only about oops, only about half of them they actually show clear offsets, and the other half we don't find any significant evidence for an offsets in them. And interestingly, the knots with offsets predominantly occur in closely aligned and higher redshift jets. So it's possible that all knots may have offsets, and projection and distance effects they simply reduce the offsets to below the detection level. And other interesting thing is here is that the distributions of these offsets and the inter-knot spacings, these suggest that these knots are probably heavy moving blobs of plasma embedded in a faster outer flow. Now these blobs could have been emitted by some kind of intermittent activity in the central engine, which is an exciting possibility, because that shows, because these jets encode whatever happens in the central engine, and if that's the case, they have direct implications to uh, the physical modeling of what happens in the central regions of the jet. Now, these considerations, they clearly suggest that we need multi-zone models, not just simple one-zone model. So what's stopping us from exploring these possibilities in detail? Simple answer, we just don't have enough counts. The first problem is that only about 1/3 of the entire X-ray jet sample contributes to the offset analysis in noise. Uh, and in even in that 1/3 sample, these jets often only contribute a few number of counts or components, like either the jet is only a hotspot or there is only one knot that shows some kind of X-ray emission. More and most of the knots are usually undetected in the X-rays because of problems with lower sensitivity. So we are essentially dealing with a highly incomplete sample, and most of the remaining jets are either very faint hotspot only detections, or they simply have scattered counts all along the jet without any clear distinct features in the X-rays. Now, offsets by themselves, then they cannot give us the full picture on how knots form and they produce X-rays. We need to combine spectral information with offsets to get the full picture. With with the with the high estimated sensitivity of axis when compared to Chandra, axis can provide answers to some several to some key questions. Mainly, it can determine the trends of some key observables as a function of distance along the jet. So first, um, the flux actually, and thereby the X-ray radio flux ratio. It's currently unclear if the X-ray radio flux ratio actually decreases along the jet or increases along the jet. Uh, in with the current sample, what we can tell is that it increases in some parts of some jets and decreases in some others, but there isn't any clear-cut picture. Now, this is important because it has implications on whether or not the jet is decelerating towards the hotspot. And second, the spectral index. It will tell us how the knots suffer energy losses along the jet, whether the losses are predominantly adiabatic or predominantly radiative, and this has implications for the collimation of the jet. And within the current sample, there are barely 50 knots that have well constrained spectral indices out of 200 jets and more than 300 knots. And third, offsets. We do have offsets in a few knots, considering the number of knots in the entire sample, but not many detections so far. And we only find a marginal evidence for offsets increasing with distance along the core. Now, this can be read as an evidence for the moving block model, but we need several more knots to actually confirm this trend. And fourth, uh, we also need to find diffuse emission between these knots, because in the moving block model, the radiating plasma, it propagates and progressively emits at uh, longer wavelengths. So by the time it reaches the end of the visible knot, it can in principle produce X-rays via ICCMB. But this diffuse emission is detected in only a few jets, and it's important to know what is the level of this diffuse emission to constrain the jet speed on kiloparsec scales. And this is achievable easily with access. Now, what I've discussed so far is only half of the story, because more than 80% of the jets are below a redshift of 1.5, and it's highly unclear how the jets produce X-rays at high redshifts, because ICCMB is expected to dominate at higher redshift due to increase in the CMB energy density, which scales as the fourth power of 1 plus z. But due to the small number of counts in most of these jets, it's hard to distinguish between different emission mechanisms. Like, is it ICCMB from the jet, or is it ICCMB from the lobe, or is it some kind of large scale thermal emission? We don't know. But axis can supply the missing spectral information here. Of course, there'll be a huge foreshortening of these jets. So ideally, we would want a better angular resolution than Chandra to understand the structure. And besides the emission mechanism problem, there is a problem of determining the statistical significance of the observed emission. Like, is it, so for example, in the central panel, there are like 5 counts in this particular feature. So is it some kind of Poisson fluctuation, or is it some kind, is it an actual emission or jet related emission? Of course, we can use a Lyra to do that, but the problem is our estimates are only as good as our simulated PSF. Now, Chandra's simulated PSF usually has a narrower core and broader wings compared to the observation. And although this can be reduced by changing a parameter in the simulation, but it's an extremely tedious job if you want to go for larger surveys. And in addition to this problem, Chandra's PSF also has an artifact that is not seen on the simulations. The observations show a 5% excess from a flux from a specific angle from the z-axis in all the observations. And this particular artifact, it can induce a false detection, especially if you are trying to detect jets that are close to the central AGN core. Now, it's also important to have a good knowledge of the PSF of axis, because in some cases, the X-ray jet may be buried within the PSF of the core, and only deconvolution will be able to reveal it. However, it is extremely hard to confirm such sources with Chandra observations because of its artifact in the PSF. Another exciting possibility with axis is that we may be able to detect X-ray jets with no radar counterparts at all, and only a few, very few instances are noted in the literature, and knowledge of, because at some point in the redshift, axis is going to hit its sensitivity limit, and we are going to be left out with only a few counts, but those are also extremely valuable given their extremely high redshift. So our knowledge of the PSF will be extremely crucial when detecting such jets with access. So to conclude, Chandra has definitely revolutionized our knowledge of X-ray jets by providing several key observations uh, at high angular resolution spanning a wide range of redshifts. But we, for the last 2 decades and more, we mostly operated in the low count regime, and that makes most of the studies inconclusive. Now, what Axis can do is it can provide really high count observations with its high sensitivity of several jets, even at high redshift, and has the potential to yield conclusive results. Uh, so what's required is ideally a very high angular resolution, ideally better than Chandra if possible, and very high sensitivity, and more importantly, a well-defined model of the PSF. So with that, I'll conclude my talk, and thank you.
Great. So if there are questions, please raise your hand. Go ahead, Justin. You can unmute and ask a question.
Hi, Karthik. Yeah, nice talk. You said the offsets, the X-ray radio offsets were greater for sources that were more aligned with our line of sight. I guess I'm wondering, because the ICCMB and synchrotron emission, they have different beaming patterns, as I'm sure you know.
Mhm.
So just wondering if there's some way that could cause the offsets. I don't have a good idea for how exactly, but I don't know, just wondering.
Actually, the knots without offsets, they predominantly appear in closely aligned jets. So
Exactly, that's
yeah,
what I'm
right.
saying. So there's more Doppler beaming. The more closely aligned it is, the more Doppler beaming there is,
Mhm.
right? So if the beaming pattern is different for synchrotron and inverse Compton scattering, I'm just wondering if that somehow that could explain it. I don't have a good idea for how, but
Yes, so in that case, actually, ICCMB X-rays would appear more amplified, and then we would expect that actually the radio decays before the X-rays, but we don't see that in these jets at all. It only happens in a very few cases, but optical observations suggest that they are probably obstacles and not X-ray emission from the jet. Uh, and also the other thing we need to take into account is that these radio emission is radio knots are at most mildly relativistic, like gamma of 1.2, but then these X-rays, they require uh, like gamma of 4 or 5 to be able to explain the observed X-ray flux. So we need some kind of velocity stratification. But when I looked at the luminosity distributions of these knots, like separating them into quasars and just normal radio galaxies, I didn't find any difference in the beaming between closely aligned jets and misaligned jets. So I don't think beaming is going to have a very huge effect here.
okay, thanks.
Great. So Richard?
Yeah, we've learned a lot, pardon me, about jets from looking at blazars. And so can you use the spectral parameters or the spectral models from blazars in this study, just taking into account their further, what you're looking at is further off angle?
Yeah, we can use the spectral information, but I don't think because the conditions in the central regions of the AGN and conditions out like kiloparsecs away are completely different, especially if you are looking for inverse Comptonized radiation. So yeah, ideally we would want to know what the emission is in the infrared, and then we build SADs out of them, and then we need to test different models that are both consistent with the spectra and also with the observed offsets. So I'm not sure if we can what we learned from blazars can be directly translated to the kiloparsec scale yet.
Okay, Herman, did you want to ask your question?
Sure, just real quick. Have you estimated whether or not X-ray jets from quasars can be observed serendipitously in random pointings rather than as part of a strategic pointing program?
No, I haven't done that yet. Yeah, but yeah, I'm still working on the simulations now. So
Okay,